This is a video on performing correlation and regression analysis. When we're doing correlation and regression analysis, we are looking at two continuous variables, continuous x and a continuous y. This is in contrast to the types of tests we've done so far. When we've done the one sample t, two sample t, or the ANOVA, what we're looking at is a continuous output, a continuous y. Remember, we're looking at the averages, so like an average turnaround time, so that's a continuous measure. But we're looking to see whether there's a difference in those averages between two or more discrete variables. So is there a difference in average turnaround time for shift A versus the average turnaround time for shift B? Continuous output, continuous Y, the time, but a discrete X, a discrete input, shift A, shift B. When we talked about proportions, we have discrete output and discrete input, discrete Y and a discrete X, right? If in the proportion tests, we were looking at whether there was a difference in the proportion of customers satisfied depending on the area that was surveyed. So the proportion was the proportion satisfied versus not satisfied. That's a binary measure versus area A, or out of area A versus area B versus area C. So the X was discrete, area A, area B, area C. And the Y, the output, was discrete, the proportion satisfied, using a binary measure of satisfied versus not satisfied. In correlation regression, we're looking at data that are continuous, both the X and the Y are continuous. And here's a famous example, right? These are length and weight tables for babies. So the idea is you can see along the x-axis, there's the age of the child in months from birth to 36. And then along the y-axis, it's kind of really two tables kind of slammed together here. You can see you have weight, which starts over here and continues on this side. And you have length here and then continue on this side as well. And so what this shows us is the correlation between age and weight and age and length for a large population of babies, a large sample of, in this case, boys. For what we're working with, we're going to be looking at some data from a call center project. So we're going to open up the correlation file. This is one of the OpEx files. Go to correlation. And this gives us the data collected from a call center. So it's focused on the answer time for telephone calls. The average answer time was reported for 80 shifts. You can see for each shift what the average time to answer was. And then we also have data collected around the number of personnel working during that shift, how many calls per hour were taken, and then how much time per call, average time per call in minutes. So you can see all of this is numeric data. It's all continuous data. So the appropriate tools to use would be correlation and regression. So we'll start with correlation. Correlation is used to measure whether there's a linear association between sets of continuous data. So if I want to ask a question about the relationship between the number of personnel working versus the average time to answer, and whether there's does it take more time to answer if there are fewer people working, less time to answer if there are more people working? What's that association between them? I would start with doing the correlation analysis. The null hypothesis for correlation and regression is that there is no association. There's no relationship between the X and the Y. The alternate hypothesis would be that there is a relationship. So do correlation analysis. I'm going to go to stat. basic statistics, and then correlation. These are all numeric values here. You can see that Minitab doesn't seem to care what order I put them in. What I've told you before is that Minitab is usually asking for the Y, the output first, and then the X. This is one place where it's reversed. It actually works better if you put the X in first, the input, and then the Y. So what I'm asking is whether the answer time is affected by the number of personnel working. So number of personnel is my X, the answer time is my Y. We'll go ahead and just do this, and then we'll have to make a change to the default settings to get the information we're looking for. So got number of personnel and answer time, click on OK. And you can see what it gives us is a scatter plot. Along the x-axis, we've got the number of personnel, and along the y-axis, we've got the answer time. And it looks like, interesting, as the number of personnel increases, goes to the right, the average answer time seems to come down. We've got the R statistic, the Pearson's R, and then a correlation, a confidence interval around that Pearson's R. Tells you how many rows used, and then it gives us that Pearson's R right there. We asked, a hypothesis, right? We proposed a hypothesis, right, that there was a relationship between number of personnel and the answer time. We don't get a p-value. We don't get a p-value by default. This is one of the more strange changes, I think, in Minitab in recent years. So I'm going to do that test again and change the default settings. So it goes basic statistics, correlation, remembers the values I put in. Here you click on graphs, and you make a change to the statistics display on plot. So here it shows you the correlation and intervals. What we want is the correlation and p-values. We want to know whether or not we should reject the null hypothesis that there was no relationship. Click on OK, click on OK again, same scatter plot. And now you can see we have the Pearson's R and we have a p-value. All right, the p-value is where we want to start. Our null hypothesis was there's no relationship between the number of personnel and the average answer time. The p is low, very low, so we reject the null hypothesis and conclude that there is a relationship. So, when there is a relationship, how meaningful is that relationship? We know it's statistically significant, but is that a practically useful result? Well, you can see just visually, it looks like the number of personnel certainly seems to affect the answer time, but the Pearson's R gives us a way of quantifying that. You can see the R here is negative 0.77. So it's important that we understand how R works. So I'm showing you here are some Pearson's R rules of thumb. So Pearson's R tells us about the strength and the direction of the relationship between X and Y. The values for Pearson's R range between -1 and +1. If it's negative, what that means is that as X increases, Y decreases. So in our scatter plot, as the number of personnel grows, the average answer time comes down, right? And our R was a negative 0.977. It's a negative value, meaning that as X goes up, Y comes down. So that's the positive or the negative, right? The sign that's in front of that R value. If it was a positive relationship, then as X goes up, Y would also go up. Positive means as X goes up, Y goes up. Great. So the sign in front of the R tells us about the direction of the relationship. The value of the R helps us interpret the strength of that relationship, the strength of that correlation. And as you can see here from the rules of thumb, if that R, the absolute value of R, is between 0 and 0.2, that's a negligible correlation. We might have a statistically significant result, but if that R, that absolute value of R, is between 0 and 0.2, it's not practically very useful. 0.2 to 0.4 is a low degree of correlation, 0.4 to 0.6, moderate, 0.6 to 8, marked degree of correlation, and 0.8 to 1.0 be a high degree of correlation. So this result here, negative 0.977, I mean, that's almost a perfect negative correlation, right? The range of values for point R is -1 to -1 to +1. That's almost a perfect -1, right? It's negative as X goes up, Y goes down, and it's very strong. It's very close to a negative 1.0. So this is a strong negative relationship. Let's look at another example from this data set here. So if we look at what's up here, if we want to look to see, is there a relationship between the number of personnel working on that shift and the time, the average time per call? You know, my theory is that if there are more people working, then there's not as much pressure to get through with a call to pick up the next call. So my theory is that if there are more people working, the operators are spending more time on those calls. They're in less of a rush to get to the next call. So I do that correlation test again. Stat, basic statistics, correlation. And again, I'm saying that the X is the number of personnel, but the result of that is the time per call. And with correlation, it just kind of works better in the output if you put the X first and then the Y. Many times remembering that I'm going to show the correlations and the p-values. Okay. Okay, again. So again, another scatter plot. You can see this isn't as tight, is it? But there's kind of a general upward slope to this. You can see as the number of personnel increases, generally the time per call seems to increase as well. My p-value, 0.00. Again, it's a very low p-value, so I can, with confidence, reject the null hypothesis that said there was no relationship between the X and the Y. And the R, the fact that it's a positive number tells me that as personnel goes up, the time per call goes up. But the value here, 0.819, that tells me the strength of the relationship. And it's not as strong a relationship as in the previous example. 0.8 is still a high correlation. It's kind of on the cusp there between a marked degree of correlation and a high degree of correlation. But it's, again, I have a statistically significant result and a result that's practically meaningful. You know, I know that I can be fairly confident that as I add more personnel, then the length of the calls will go up. Maybe that's a result that I want. Maybe that's something I'm looking for. So the one test we've done so far is the correlation analysis. What about the regression side? Well, let's talk about what regression means. Correlation tells us about the strength and the direction of a relationship. Regression tells us about how much of the variation in the Y, in this case, the time per call, is attributable to the X, number of personnel. So we've done our correlation. I'm going to go ahead and do the regression analysis on this same data. So we go to stat, regression, and we're just going to do a simple fitted line plot regression. Here is the one place in Minitab where it actually labels your Y and your X, your response and your predictor. So in my theory, I'm saying the number of personnel affects the time per call on average. So my response is time per call. My predictor is number of personnel. Click on OK. You can see it, the output is a little bit different. Here's the fitted line. It's basically the same fitted line. Number of personnel, as number of personnel goes up, the time per call goes up. So this scatter plot looks very similar, but by doing the fitted line, it actually puts the line on there. And what it does is it shows us the slope of that line. Now, I said before that the null hypothesis in correlation and regression analysis is basically the null hypothesis. There is no relationship. Technically, that null hypothesis is there is no difference between the slope of the line and a slope of 0. But I think it's fine for us to use the null hypothesis. There is no relationship. So we can see that clearly the slope of the line is not 0. But what's our p-value? Well, it's still 0.00. It's the same. You got the same p-value from the regression analysis as you'll get from the correlation analysis, right? So here's your p-value. It's statistically significant. Is this a practically meaningful result? Well, the R squared here is 66%. We use the R squared adjusted, 66.7%. What that tells us is that 66.7% of the variation in the time per call is attributable to the number of personnel. That's a good deal of variation attributable to a single variable. So let's look at the R squared. Previously, we were using R. For correlation, we use R. For regression, we use R squared. But let's look at the rules of thumb for R squared. So R squared, sometimes referred to as the coefficient of determination, tells us what percent of the variation Y is due to X. So when we're interpreting R squared, anything that's less than 40%, we'd say is not predictive. Anything that's between 40 and 64%, mildly predictive, 65 to 84, moderate, 85 to 100, strongly predictive. So what was this? This was 66.7. So that falls into the moderately predictive camp. What that means is that we can't say for certain, based on the number of personnel, exactly how long the average call will be. But it is moderately predictive. There may be other factors in play that prevent us from making that prediction just based on the number of personnel. One of the things that's particularly useful in doing the regression analysis is not only do you get a fuller picture of how useful that analysis of the relationship is, you actually get a regression equation here. So you can see the fitted line plot, the equation that produces this fitted line plot is the time per call in average minutes is equal to minus 2.88 plus 0.08119 times the number of personnel. So you plug in the number of personnel, and then what you'll get is a predicted time per call. Now, the R squared tells us that we're not going to get an exact number, but we'll get somewhere within a reasonable range. If we look at the regression analysis for the other relationship that we looked at, regression fitted line plot. In this case, what we're looking at is whether the time to answer, whoops, whether the time to answer can be predicted by the number of personnel. Remember, we had a strong negative relationship. So as the number of personnel went up, the answer time went down. We have the same p-value, 0.00. So we know that we can reject the null hypothesis and conclude that there is a relationship. The R squared tells us that the number of personnel is strongly predictive of the answer time, or the time to answer for those calls. With a high R squared, I can plug in the number of personnel in this equation and get a predicted answer time that's going to be pretty close to the observed answer times here. So what does this tell me practically? Well, if I do nothing else with this process, don't change any other of the methods or any of the equipment or anything else, but I just add more personnel, I can continue to bring down that answer time. So it tells me if I need to achieve a certain answer time, how many people I would need to throw at that process. Again, that's assuming that I don't make any other changes to the process. And as we know, most improvement projects require you make changes to that process. But it gives us a good sense of, what will happen if there are changes in staffing. And there are invariably going to be changes in staffing. People will be out sick, people will be on PTO, vacation, whatever. When you hire someone, it takes some time before they get, fully up to speed. So that's going to affect your effective number of personnel. So this slide shows some different scenarios from this data. Here we've got a couple of the questions we looked at, whether the number of personnel affects the answer time, whether the number of personnel has a relationship with the time per call. The third one, which we didn't do, but you can do on your own, is whether the number of personnel affects the number of calls per hour. Here we see the results, the p-value, which is going to be the same for the correlation and for the regression test. In this one, there's a p-value of 0.00, which means we reject the null hypothesis, right? That's statistically significant. The R is negative 0.977. We would interpret that as a strong negative correlation. The R squared is 95.4%, strongly predictive. So in terms of, how useful this is, we'd say this is a critical X. The number of personnel is a critical X. We're looking at the average time to answer calls. We're going to look at the next question, whether personnel is a critical X for the time per call, how long calls last. Again, we've got our p-value, 0.00. We reject the null. There is a relationship that's statistically significant. Pearson's R tells us that it's a positive correlation and there's a marked association between them. And then R squared tells us that about 67% of the variation in time per call is predicted by the number of personnel. And we characterize that as moderately predictive. Not strongly predictive, moderately predictive. So that's possibly a critical X. But, there might be something else that we would look at. If we're looking to affect the time per call, number of personnel would not be the only place that I'd look. And then down here, we have the results. We look for the association between number of personnel and number of calls per hour. Our p-value 0.106. It's not statistically significant. We would fail to reject the null hypothesis. And we'd say there's not a relationship between the number of personnel and the calls per hour. The R and the R squared follow right along. The R, it's a positive number, but it's a very low number. And using our rules of thumb, we'd say that's a negligible correlation. R squared is 3.3%. 3.3% of the variation in calls per hour can be predicted by the number of personnel. That is not predictive. So we have p-value that tells us that there's not a statistically significant result. Fail to reject the null hypothesis. The R and the R squared clearly go along with that. Our conclusion would be that number of personnel is not a critical X when it comes to the number of calls per hour. So correlation regression can be powerful tools when you've got continuous X and a continuous Y. We do the correlation analysis to determine the strength, the direction of the relationship. The regression analysis tells us how predictive the X is of the amount of variation in Y. And of course, the p-value lets us know whether there is no relationship between the X and the Y, or if it's a low p-value, you can reject that and conclude there is a relationship. The regression equation that we get from doing the regression analysis and the fitted line plot, when you have a scenario with a strongly predictive relationship, that regression equation can help determine what result you would expect to get depending upon the level of your input. So powerful tools, and also very useful, particularly when you can get your data, you can collect your data in a continuous format. You can do the most powerful kinds of analysis with that kind of data.